In this lesson, we are going to learn about mass defect and binding energy. Let us consider a nucleus like the sodium nucleus. Atomic number of sodium is 11. So it has got 11 protons. Mass number of sodium is 23. So it's got 12 neutrons. Right? Now, what will be the mass of the sodium nucleus? Will it be equal to the sum of the masses of 11 protons and 12 neutrons? Will it be more than that? Less than that? Now, some of you may think that sodium nucleus is having 11 protons and 12 neutrons. Therefore, its mass is same as the mass of 11 protons and 12 neutrons. Some of you may think that there are 11 protons and 12 neutrons inside this nucleus. Some extra mass may be there to cover the nucleus. So, mass of the nucleus will be more than the mass of 11 protons and 12 neutrons. Both are wrong. Actually, the mass of sodium nucleus is less than the sum of the masses of 11 protons and 12 neutrons. You may wonder why. Ultimately, there are 11 protons and 12 neutrons are here. So, how come the mass of the sodium nucleus is less than the mass of 11 protons and 12 neutrons? Actually, some mass is lost in the formation of nucleus. This mass lost is called mass defect. Mass defect delta M is equal to mass of separated nucleons minus mass of stable nucleus. So, any nucleus has got how many protons? Whatever is the atomic number, right? Z into mass of protons. How many neutrons are there? A minus Z. A is mass number, Z is atomic number. So, A minus Z is the number of neutrons. You multiply this with the mass of neutron. So, this gives the mass of separated nucleons. And then we subtract the mass of stable nucleus. And that is what is the mass defect. Please understand this very carefully. This has got 11 protons, 12 neutrons. But this mass of this nucleus is less than the mass of 11 protons and 12 neutrons. Some mass is lost in the formation of the nucleus, and that is called mass defect. Imagine you are God. You are making the sodium nucleus. You got 11 protons with you, 12 neutrons. You bring them together. Make the sodium nucleus. You will find that the mass of sodium nucleus is becoming less than the mass of 11 protons and 12 neutrons. This mass defect is actually converted to energy. This is the energy released in the formation of nucleus. That we call it binding energy. The energy equivalent to mass defect is called binding energy. So, binding energy will be equal to mass defect into C square. As per mass energy equivalence, E equal to mc square. So, binding energy is delta M into C square. This is the energy released in the formation of the nucleus. The other way to think of binding energy is the energy that you need to give to a nucleus to separate the nucleons. So, here got again, right? You have to convert this sodium nucleus to 11 protons and 12 neutrons. So, what did you do? You supply binding energy to this nucleus. And then you will get 11 protons plus 12 neutrons. So, there are two ways to understand binding energy. One is It is the energy released in the formation of the nucleus. The second way, it is the energy required to separate the nucleons. Now, how do you calculate binding energy in a question? Normally, the mass will be given in unified atomic mass unit. So, binding energy will be equal to delta M in U, the mass defect in unified atomic mass unit, and we multiply this by 931.5, and this much MeV of energy will get. This is how we calculate binding energy. Now this mass of nucleus is not easy to measure. We can measure the mass of an atom easily, but not the mass of a nucleus. So we modify this equation to make life simple, calculation easy. So what we do, here we add Z electrons. Proton plus electron will give us hydrogen atom. So we'll multiply Z with mass of hydrogen atom. This we keep it unchanged. So A minus Z into mass of neutron. And now here also we add Z electrons. So this nucleus becomes atom. There is some error in doing this, but that we can neglect for the time being. So this is how we will calculate mass defect. Z into mass of hydrogen atom plus A minus Z into mass of neutrons minus the mass of stable atom, that is mass of nucleus along with the electrons. This will give us mass defect. And when the mass defect is in U, we can multiply that by 931.5, and that will give us the binding energy in MeV. So in this lesson, we learnt about mass defect and binding energy. When a nucleus is formed, some mass is lost. That is called mass defect. The equivalent amount of energy is called binding energy. So binding energy is the energy released in the formation of nucleus. Binding energy is also the energy required to separate the nucleons. Binding energy is not there in this nucleus as some energy. It is the energy that has been released. That is not there. Okay, you need to give it this much energy to separate the nucleons. Mass defect we calculate by this formula. Mass defect is mass of separated nucleons minus mass of stable nucleus. Because measuring the mass of nucleus is difficult, we use this equation, mass defect equal to Z atomic number into mass of hydrogen plus A minus Z, that is the number of neutrons multiplied by mass of neutron, and minus the mass of atom. So this is mass defect. And mass defect in AMU or U, you multiply by 931.5 and you get the binding energy in MeV. Now we'll solve two problems on mass defect. This is one reaction that is given to us. Neon 23 becomes sodium 23 plus beta minus particle and an antineutrino. Right, this is beta minus decay. The question is, find the minimum and maximum kinetic energy of the beta minus particle. Minimum kinetic energy is always 0. If this antineutrino runs away with all the energy, then beta minus particle is left with 0 energy. So minimum kinetic energy is 0 MeV. Maximum kinetic energy we'll get from mass defect. Mass of these two we can forget, they are very, very small. So mass defect we'll get by subtracting this from this, 22.9945. right, minus 22.9898. So what do you get? This is 5. So we get 0.0047, this much U. This is the mass defect. How to find the energy? Multiply this by 931.5. That will give you MUV. We can divide by U so that this equation looks nice. And that comes to 4.4 MeV. And this is Kmax. So in this nuclear reaction, the minimum energy we can get is 0. Minimum energy of the beta minus particle. And the maximum energy of the beta minus particle is 4.4 MeV. How did you get that? Mass defect, mass of this minus mass of this, that came to 0.0047 U. Multiply that by 931.5 and you got the answer as 4.4 MeV. Very, very easy. Let's look at one more problem. These 3 alpha particles are combining to form carbon 12 nucleus, right? So what is the energy released in this nuclear reaction? The mass of helium nucleus is given. Helium nucleus is nothing but alpha particles plus electrons. So therefore, we got the atomic mass of helium. Carbon 12 has exactly got a mass of 12 U, because that is the definition of U. Okay, 112, the mass of carbon 12 atom is known as 1 U. So therefore, in this reaction, the mass of the reactants will be 3 times this. So multiply this by 3. So what do you get? 12.007809. The mass of the product is exactly 12 U. So what do we get? 0.007809. This is the loss in mass, exactly 12, right? And how to convert this to energy? Multiply this 0.007809 by 931.5. This will give you 7.27 MeV. So this is how you solve problems on mass defect. Mass defect is mass of reactants minus mass of products. So find the difference in mass in unified atomic mass unit. Don't bother if the mass of the atom is given in place of mass of nucleus, because the electrons cancel out. Once you have got the mass defect delta M in AMU, multiply it by 931.5. That will give you the energy released in the reaction in MeV. As simple as this. Very, very easy. Remember, all of physics is easy. Just learn the basics correctly.